I want to go through our problems from section 14.6 and section 14.7 that all have to do with the function f of x comma y is x cubed minus 3xy plus y cubed. To start, we're asked to find the equation of the tangent plane to this surface at the point 2, 2. Well, I'm going to start by reimagining the surface I'm talking about as a level surface to a function on 3 variables. So I'm going to imagine that this is a z and subtract it to the other side. So this would be what I would get. I'd get 0 equals this function on 3 variables. So the surface I'm dealing with here is the level surface to this function at w equals 0, setting this equation equal to 0. I know that a tangent plane is always normal to a level curve, so I can find del big F by taking partial derivatives. And of course, this last partial is minus 1. And we can actually memorize this as a special rule. I like always doing it the same way, where I approach this as a tangent plane to a level surface of a function on 3 variables. Next up, I need to evaluate my gradient at the point 2, 2, the z coordinate. Now, my gradient here doesn't really depend on z, but very technically a function on 3 variables, and I'm going to have to know the z coordinate anyway. Well, going back to my original surface, little f of xy, plugging in 2, 2 will reveal that the z coordinate is 4. So now I just need to evaluate this gradient at 2, 2, 4, and plugging in 2's for x and y will give me the vector 6, 6, minus 1. So I know my tangent plane will be 6x plus 6y minus z equals some number that I usually think of, or I usually call d, where d is the dot product between that normal vector and a vector pointing at the point 2, 2, 4, the point I know is on my tangent plane. Let's see, I do this dot product and I'll get 12 plus 12 is 24, plus a minus 4 is 20. So there is my tangent plane. In problem number 2, I'm asked to write down the linearization of f of xy at that same point. Well, I know my tangent plane is the equation 6x plus 6y minus z equals 20. A linearization is just the tangent plane. So I just need to solve for z. So I can add z to both sides and take 20 away from both sides. And here is my linearization, the standard linear approximation of the function. All right, so I have my linearization. Number 3 asks us to to find the total differential of f at that same point. That requires me to know a definition, that df is the partial with respect to x dx plus the partial with respect to y dy. I could just as well call that dz. Well, at the point 2, 2, I've already established that this is a 6. And this is also a 6. So here's my total differential at the point. df is 6 dx plus 6 dy. And this really establishes that df, a dependent variable, is relationship with dx and dy, independent variables. Finally, number 4 asks me to find delta z and dz as the point 2, 2 changes to the point 2.1, 2.3 in the domain. So my point goes from being 2, 2 to being 2.1, 2.3. Well, delta z is easy to calculate. I just need the 2 z values. Well, I know that f of 2, 2 is 4. So now I just need to plug in 2.1 and 2.3 to the original function. And you can pause the video here and make that calculation because you don't need me to plug that in. But once you have, you'll find out that it comes out to be a 6.938. So delta z, the difference in these two values, the second value minus the first value, I get 2.938. dz is calculated using my total differential. 6 times a change in x plus 6 times a change in y. It's convenient that my partials here were identical. They certainly don't have to be. Well, delta x and dx, delta y and dy are talking about the same thing. So the change in x is 0.1, the change in y is 0.3. And after doing the multiplication, I find out that dz is 2.4. The whole idea here is I can use dz to approximate delta z. Delta z is the actual change in the z coordinate as I move from one point to the other point on the function. dz is the change in height as I do the same thing with respect to the tangent plane. The same way that a differential was approximating the change in a function in Calc 1 using a tangent line. Okay. Next up, we're asked to find all the local extreme values and saddle points of that same function. So f of xy is still x cubed minus 3xy plus y cubed. Well, if I'm going to find all of the local extreme values and saddle points, I'll need to know all of the first and second order partial derivatives. I've already found the first order partials when I wrote down the gradient. I can go on and find my second order partials. Here, differentiating with respect to x again gives me a 6x. Here I'll have a 6y, and then a mixed partial. And I really only need one of these because I know they're going to be the same. Since they're so easy to do, I'm just going to write them both down anyway. I always enjoy writing them both down, and that's probably an odd thing to say and then publish on YouTube, but whatever. All right, I get minus 3 for both. Clairaut's theorem is always a good thing to remember. Okay, so now I need to look for critical points, which means I'm looking for places where my partials are identically equal to 0, where my gradient vector would be 0. Right away, I see I could imagine dividing everything by 3 in both equations, so simplifying everything just a little bit. Next, I think I'll solve this equation for y. And then I can substitute it into this equation. So I would have minus x plus, well, if I plug in x squared and then square it, that'll be an x to the 4th. Well, I'm going to imagine factoring out an x. That would leave me with an x cubed minus 1. I can factor that using the difference of squares formula. Difference of cubes formulas, excuse me. This gives me two real zeros, x equals 0 and x equals 1. I happen to know that this gives me complex solutions. You can check that out if you want using the quadratic formula. But here are my only two real x values. To find the corresponding y's, I think it's easiest to use this equation. So the only critical points I'm going to have are at 0, 0, and 1, 1. The second derivative test for local extreme values says I'll need to know this value to know if I have a min or a max happening, and I'll need to know the value of the discriminant, also called the Hessian. H of xy, the discriminant, the product of these two things, so 36xy, minus the product of these two things, which is 9. All right. So what I want to do now is build a table where I evaluate fxx at both critical points and the Hessian at both critical points. All right, well, and just a reminder, the second partial with respect to x is just 6x, and the Hessian is 36xy minus 9. So, I actually don't need to evaluate the second partial with respect to x for this one, because if I plug in 0, 0, I'll get out minus 9. And I know when the discriminant is less than 0, I have a saddle point. So right away, I can tell you there's a saddle point at 0, 0, and I need a z-coordinate there. And if I look at the original function, it'll zero out. So the saddle point's at 0, 0, 0. When I talk about mins and maxes, I give you a z value that is the min or max, and then the place in the domain in an ordered pair. For saddle points, we're going to list the x, y, and z that's actually on the surface. Now, just for the heck of it, I can write a 0 in there. I didn't need to evaluate that. I've already figured out that that's a saddle point, or that this point gives me the location of a saddle point, but I might as well. All right, plugging in 1, 1, I'll get out 27. So the sign here is going to tell me whether I have a min or a max. In the x direction, if I looked at this, I'd be getting that concave upward shape, telling me that this is where a min occurs. There is a local min of some number at the point 1, 1. Well, f of 1, 1, it's 1 cubed minus 3 times 1 times 1 minus 1 cubed. Plus 1 cubed looking at the original function, and I get 2 minus 3 is minus 1, so that local minimum value would be minus 1. These are my only two interesting points. Here's my only local extreme value, and here's a saddle point at the origin. Finally, we're asked to find all the absolute extreme values of f of x, y over a square in the first quadrant that has corners 0, 0, 0, 2, 2, 2, and 2, 0. By reducing the points we're allowed to use to this closed region in the plane, I not only can have local extreme values, I am guaranteed to have absolute extreme values. Here are the points listed. So, what we are told is that we can have these absolute extreme values at critical points in the interior. Well, in our last problem, we found out there was a critical point at 1, 1. So that's on the interior. There's also a critical point at 0, 0, but that's not on the interior, it's on the boundary. I'm going to have to check it anyway in a minute for a different reason, but I'll definitely have to check 1, 1 because it's a critical point on the interior. The other places I'll need to check, right, the only interior points I have to worry about are that critical point. Now I have to worry about what's going on over the boundary. The function z equals x cubed minus 3xy plus y cubed. If I plug in, if I imagine looking at what happens just at in the plane defined by y equals 2, right? I imagine that I can have this plane come out and it intersects the surface, right, in a curve. Well, that curve will be continuous. So over this boundary element, my curve will have both an absolute max and an absolute min that could happen at the endpoints, right? Maybe it has some shape like this, or at a critical point in there. And that's just first calculus. That's using the extreme value theorem just over the places where y equals 2. So the places I need to look, critical points of the interior, critical points over boundary elements, and then the endpoints of the boundary elements, which I can see are just the corners. So first up, we found our critical point. Now I want to find the critical points over the boundary elements. The endpoints are easy. They're the corners of my square. So I'll put those in last, but I already know what they are. So let's just reduce ourselves to caring about what happens when y is equal to 2. Well, when y equals 2, my curve becomes x cubed minus 6x plus 8. Well, this is really a function on one variable. You plug in an x, you get out a z, right? So I'm imagining, again, a plane coming out of the board and intersecting my surface. Well, it's a cubic function. So what I need to do is take a derivative. And I'm just going to imagine I live in this plane where y equals 2, and I'm just going to write that z prime is equal to 3x squared minus 6x. Excuse me, just minus 6, taking the derivative of that linear bit. If this has critical points, it would be where I have mins and maxes on this particular function. This is really a partial derivative because I fixed y to be 2. Because I'm just imagining living in that plane, I'm just going to call it z prime. 0 equals 3x squared minus 6. 6 equals 3x squared. X squared is equal to 2, so x is either plus or minus root 2. Okay, well, nicely enough, I only have to worry about the plus part because my x's and y's are clearly bigger than 0. So I get 1 point to check out here. X is root 2 and y had to be 2. And let's think about where that point lives. Square root of 2 is about 1.414. So that critical point would be right about here. The other one would be out here. Okay, so that checks everything I need to know about the y equals 2 part. Let's move on and see what happens where x is equal to 2. Well, I get 8 minus 6y plus, I get the same thing except for in the variable y. And again, I'm reduced to one variable. I am really thinking about taking a partial with respect to y because I fixed x. And I'm going to end up having found the same critical points. And again, y is plus or minus root 2, but I can get rid of the minus because all of my y's are bigger than 0. And so x is 2 and y is root 2, so I'll need to add those to my table. Okay, I have 2 more boundary elements to inspect, and I've kind of run out of room on this board. So I'm going to move it to the side and inspect what happens at x equals 0 and y equals 0. Spoiler alert, those 2 boundary elements aren't that interesting. So we're going to come back to this board in a minute. So I need to worry about x equals 0 and y equals 0. My function f of xy is x cubed minus 3xy plus y cubed. Well, if x is 0, I just end up with a y cubed. I take a derivative, and I end up with a 3y squared. I set that equal to 0, and I'd get out 0, 0. And I was going to check that point anyway because it's one of my corners. Let y equal 0, I'm going to get z equals x cubed. And again, set this derivative equal to 0, and I'm going to get 0, 0. And I was going to check that point anyway because it's one of my corners. All right, so all together now, I have to check 1, 1 because it's a critical point of the interior. I have to check these 2 points because they're critical points over boundary elements. And then I have to check all 4 corners because they're the endpoints of my boundary elements. So, off camera, I'm writing down everything I'm going to have to check. And then I'm going to write down the z values. The largest z value I write down belongs to my absolute max. The smallest z value I write down is the absolute min. So, 1, 1's a critical point. Root 2 comma 2 and 2 comma root 2. Those are boundary elements, critical points over boundary elements. And then I need to write down the 4 corners. All right, there they are. And I need to write down the z's. And f of xy was the function x cubed minus 3xy plus y cubed. So I need to fill in this table where I have 1, 2, 3, 4 points that are in there because they're endpoints of my boundary elements, the corners. I have 2 points that are critical points over boundary elements, and then 1 point that is the critical point of the function itself, critical point on the interior of the domain. I happened to use GeoGebra earlier to evaluate these points, so I'm just going to write down their z-values. It's not a bad idea for you to pause the video and fill this table in yourself, but I'm going to go on and fill it in. So at 1, 1, we get out a minus 1, and we know that from our work from part 5. Root 2, comma 2, I get out 2.34. At 2 comma root 2, I get out 2.34. At 0, 0, I get out 0. At 0, 2, I get out 8. At 2, 2, I get out 4. And finally, at 2, 0, I get out 8. The largest thing in my table belongs to my absolute max. That happens twice over this particular domain. And then this value must be my absolute min. The absolute min minus 1 occurs at 1, 1. The absolute max of 8 occurs at 0, 2, and 2, 0. And now we have found our absolute extreme values over that closed region in the domain.